All right, so this is the second part of section 8.2. This is on graphing the other trig functions. So in 8.1 we graphed sine and cosine because they were very similar. Now we're going to talk about graphing the rest of them. So picking up where we left off, example 2, we're going to graph tangent of the quantity x plus pi over 4. So with these, it's a little bit easier to graph them using asymptotes. Right? So on your formula sheet, remember how I gave you the vertical asymptotes for one period of each of the functions as a guide to use. So if we take this argument of the tangent function, that's the thing you're taking the tangent of, and we set this equal to the original vertical asymptotes of negative pi over 2 and pi over 2, we will find the new asymptotes. So just a little bit of algebra here. Taking x plus pi over 4, that argument, setting it equal to negative pi over 2 and pi over 2. To solve both equations, we're going to have to subtract pi over 4 from both sides. This is the equivalent of negative 1/2 minus 1/4, which is negative 3/4. The pi kind of acts like a variable. Like if you were adding 3x plus 2x, you'd get 5x. So pi is kind of acting like a variable here. Same thing over here. We subtract pi over 4 from both sides to solve this equation. This is 1/2 minus 1/4, which is 1/4. The pi is along for the ride. So my new vertical asymptotes for this equation is negative 3 pi over 4 and pi over 4. So let's graph those, and then we'll get everything else from that. So negative 3 pi over 4, pi over 4. The tangent graph, we know, has this shape to it. So where is this 0 located? Where is that x-intercept located? Well, it's halfway between the asymptotes. And remember how I said we can find the halfway point by just adding them up and dividing by 2. So if we add up these two endpoints and divide by 2, we get the midpoint, which in this case is that intercept. So I added these two together. Now this, I just kind of took the pi out of it to make it maybe a little easier for you and to show you could do it on your calculator. So that negative 3/4 plus 1/4, negative 2/4 divided by 2. That reduces to be negative 1/2, and then divided by 2 is the same as times 1/2, so I got negative 1/4. Coming back up here, throwing the pi in there, because there's that understood 1 right there. That negative pi over 4 is my 0 there. And it has this shape because it's a tangent graph that was not flipped or twisted in any kind of way. Okay, so example 3. This is a cotangent graph. This is what we call the amplitude for the sine and cosine. But for the cotangent, it's just going to be a stretching factor, kind of in the same way the amplitude was a stretching factor. We're going to take this argument and we're going to set it equal to the original vertical asymptotes for cotangent, which you can get from the formula sheet. Those are 0 and pi. So setting 2x, that argument, equal to 0 and 2x equal to pi, because this is multiplication, that smushing right there between the 2 and the x, to solve that equation we have to divide both sides by 2. So I get the two new vertical asymptotes are 0 divided by 2, which is 0, and pi divided by 2, which is pi over 2. Alright, so we graph those. The cotangent has this shape. If you forget about the shapes, remember I gave you the graph of these. So cotangent goes like this, tangent goes like that. So the cotangent graph is going to do this. We have those two asymptotes, one at 0, one at pi over 2. The halfway point here is my intercept. Halfway between 0 and pi over 2 is at pi over 4. You can add those up and divide by 2. And then these halfway points in here those are where that 3 and that -3 come into play. That's going to show you how much the graph was stretched or compressed, right? Normally, these would be at 1 and -1, but because this has been stretched and because, you know, my scale is way off here, it's going to be up here, 3, -3. So I just wanted to kind of show you where that 3 and -3 kind of come into play here. That point right there would be pi over 8. So that's, you know, 1 pi over 8, 2 pi over 8, 3 pi over 8, and that would be 4 pi over 8 right there. Okay, so basically we're going to use this to help us with the general shape of the graph, and we're going to use it for what the original vertical asymptotes were. So we're going to graph these by finding the new and improved vertical asymptotes, and then everything else is going to fall into place. Okay, so cosecant graph. Let's take the argument. The argument is the thing you're taking the cosecant of. Okay? So we're going to take that argument and we're going to set it equal to the original vertical asymptotes for one period of the cosecant function. Those happen to be -pi, 0, and pi. Remember, the cosecant and the secant have 3 vertical asymptotes to them. All right, so 3 equations, all solved in the very same way. So, see, the argument 2x, I set it equal to -pi, 0, and pi. Similar to the last example, that's 2 times x, so we solved that by dividing both sides by 2. So that's where this 2, and this 2 came from. It came from me solving that equation. So the equation there was that 2x equals -pi, right here, and I just divided both sides by 2 to solve that equation. So here's my 3 brand new vertical asymptotes. I graphed those. So -pi over 2, 0, and pi over 2. The halfway points were a little easier to find because of this 0 right here. Okay? So because that's 0, halfway between 0 and -1/2 is -1/4. Halfway between 0 and 1/2 is 1/4. Then going back to our formula sheet to see what the cosecant looks like. Right there. It is a down and then an up. So we have down and up. But that 3 up there changes it to where this little, you know, kind of local min here is at 3, and this kind of local max right there is at -3. This does not have any x-intercepts. The cosecant and secant graphs, unless they've been shifted up or down, won't. All right, let's move along here. And let's do a secant graph. Okay, so we're going to take that argument of the secant function, that x plus pi over 2, we're going to set that equal to the 3 original vertical asymptotes for the secant function. Okay. So taking that argument and setting it equal to -pi over 2, pi over 2, 3 pi over 2. Because this is a plus, to solve that equation, I need to subtract pi over 2 from both sides. These are same 3 equations, just with these numbers up here being different, so I'm going to subtract pi over 2 from both sides of each one of these. So I'm solving these one at a time. I'm subtracting pi over 2, I get x equals -pi. Because that's -1/2 minus 1/2. Okay? This is 1/2 minus 1/2, which is 0. This is 3/2 minus 1/2, which is 2/2, or just 1. You can really think of the pi like a variable here, like you're just kind of combining like terms. So here's my brand new vertical asymptotes. All right, so I've got -pi, I got 0, and I got pi. Because of this 6 up here, we know that this little local min and this local max here are going to fall at 6 and -6. these halfway points. Well, this is halfway between 0 and 1. Halfway between 0 and 1 is 1/2. Halfway between 0 and -1 is -1/2. So those worked out pretty nice. So you'll notice I have like little kind of diagonal lines here. That's because an asymptote is kind of hard to see on an axis. So that you can see it on the axis, I make those lines kind of like that. So if you wonder what I'm doing there. Okay, so I've got all the important parts here. The shape of it is a secant graph. So my graph goes up and then down, whereas the cosecant goes down and then up. So it goes up and then down. And we know this is just one period. There's other stuff happening over here. We know that there's another down over here. There's another up here. But there's just the one period that we're after. All right, let's do one more, and then this section will be done. So -3/2 cosecant pi x. Just like every single time with these that have these vertical asymptotes to them, the easier way of doing this, it's not as nice as like the sine and the cosine where you can adjust the period and the amplitude and stuff. These, it is just so much easier to just change the asymptotes and then everything else falls into place. Okay, so cosecant. So we come over here, cosecant, -pi, 0, and pi. All right, so we're going to set this equal to -pi, right? So pi x equals -pi. You solve that by dividing both sides by pi, you get -1. Okay, let's set pi x equal to 0. Divide both sides by pi, we get 0. Let's set pi x equal to pi. Divide both sides by pi to solve it for x, we get x equals 1. These are some really nice asymptotes, aren't they? That almost sounded inappropriate there for a hot second. So my asymptotes here are at -1, 0, and 1. The pi's went away. Halfway between 0 and 1 is 1/2. Halfway between 0 and -1 is -1/2. Those halfway points were pretty easy to find. And then these blue things right here, that 3/2, that comes from right here. Blue pen. So that 3/2 right there is where these come from. So what does this negative do? What does this highlighted negative do for us? Well, let's look at what the cosecant graph did look like. Okay, normally the cosecant graph goes down and then up. So I just kind of, whoop, whoop. But because we flipped it, okay, this down whoop, flips to be up, and this up flips to be down. Okay, that's because of that negative out in front. That's what told me that I'm going to need to flip both of these across the x-axis. It's a reflection across the x-axis. All right, that finishes us up for section 8.2.